Last September 1st, Saturday morning, we had a very interesting meteor shower that was visible from people in the local area. All you needed to do was just go outside, look up at the sky, and you could see these meteors. And this was a very special shower because it was the first time ever we were able to predict this type of shower. They are caused by comets that go in long orbits, that come back only less frequently than once every 200 years. This particular one was the last time at the Sun 2,000 years ago. It let go of some dust particles, comet and dust, then moved back all the way to the Oort cloud, far beyond Neptune. The dust came back, comet came back, but the dust made a little bit of a wider orbit than the comet because it was pushed out by the light of the Sun. And so the comet came back first, and that happened in 1911. And the comet at that time was seen by and discovered by a postdoc at Lick Observatory called Carl Kies. Just by accident, just a few days after a bad earthquake damaged Lick. He found this comet, which now carries his name. Now the comet came back in 1911, but the dust has been coming back ever since. There's this continuous stream of dust sitting normally just outside of Earth's orbit. Now, once in a while, the planets steer this dust in the path of the Earth. And when that happens, very briefly, for only about an hour and a half or so, we see a very nice meteor shower in the sky. And everything has to come together because the trail is very thin and it has to be right there when the Earth is at its point. And circumstances are not very often that that's the case. And for this shower, it was predicted to happen on September 1, and it did.
And how good was it? Pretty nice?
It was beautiful, yeah. Everybody who actually stood up in the morning, sort of against common beliefs, because there was a bad moon in the sky, and it was early in the morning, and people weren't worried that it might not show, because the trails are so thin. People that actually did go out had a beautiful time. They saw some of these little specks that dated 2,000 years ago. Every single little piece was released around 4 AD, take 40 years. The interesting thing about meteor showers is that they are great if you can see a lot of them. And so you want to put yourself in a place that you see many, many meteors. And one thing you can do is you can go to a dark place, away from city lights, away from smog, to watch the meteor shower. What you can also do is buy a ticket to somewhere, fly in a plane, be high above the clouds and be high up in the atmosphere and look at the shower near the horizon. Because if you're on a plane and you look out over the horizon, you're monitoring a very big surface area. And there's very little dust and air between you and the meteors. And so you have a very good view of the shower. And last September 1, we got an opportunity to do that. We actually were given a chance to fly 2 Gulfstream business jets with a team of 24 of us researchers to be above clouds, to monitor this area over the horizon and look at this meteor shower. And we had a ball. It was just fantastic to see that many meteors in a short period of time.
Can you also explain the piece of the meteor is over here?
Yes. When a meteorite comes down, it looks like this. You can recognize a meteorite because from the inside it's grayish color. This particular type of meteorite, it's a grayish color, but it has this really thin, dark, black, what we call a fusion crust. And this is because the meteorite went all the way through the atmosphere and got very, very hot in the process, with material ablating off. What this layer is a thin layer of glass. And it's brown because of iron in the meteorite. And so this little thin layer of crust is what gives away a meteorite. I brought these meteorites to tell a story about what meteorites are, what asteroids are, how they hit the Earth, and what types of materials are produced by doing so. This rock is what we call an ordinary gondrite. It's a primitive meteorite which still contains all the materials that the solar system was made of, except for the very volatile ones like hydrogen, helium. Much of the carbon has been lost from this, but most of it is primitive. It's made up of little bits and pieces that originally came together to make this rock. So this is the sort of the beginning stage. Many asteroids are made out of this stuff. Now, if the asteroid gets really big, and is hit by another asteroid, it can melt. Then the heavy stuff can sink to the core, and the lighter stuff, the froth, can come to top and drift out at the top and form a crust. That's the situation with the Earth. So the Earth had the iron sink to the core, and the froth, or what we call the soil,
Okay.
come up to the surface. And those asteroids that are not well mixed anymore, but are differentiated, can also smatter into bits and pieces when they are hit again by another asteroid. And those bits and pieces give us other types of meteorites. The core of an asteroid, the stuff that sinks to the bottom, gives us the iron meteorites, and this is an iron meteorite.
Okay.
It's not only made up of iron, but there is also a significant amount of nickel in it, and it cooled very slowly. And when there's a lot of nickel in the iron and it cools slowly, the nickel has a way of wanting to be in certain ratio with the iron atoms, and so a lot of nickel will move in one direction and will evacuate other areas. So it really crystallizes in two different types of material. And if you put this iron meteorite in a little bit of acid, you can etch away one of those two minerals. And the result is this interesting pattern of lines and stripes, the Whitman-Stetton pattern. And this is how you can prove that indeed the piece of iron you have in your hand is a meteorite. Now this material is what is at the core of the Earth. Normally, by the way, the iron meteorites, when they come in the atmosphere, they explode and they shatter all this shrapnel on the ground. And this is really how you find iron meteorites when they've freshly fallen. So it really looks like a grenade went off. This little piece is a type of meteorite that forms in between the mantle and the core. It's where rocky material sinks into the iron core, and it's called a stony iron meteorite. It has these really big crystals in it, green colored, which we call olivine, inside the iron that's there. And it's a beautiful rock. It's just a fantastic feat of nature to make this beautiful material. But this is really little pieces of rock that sank into the core of the asteroid that then later smattered into smithereens. Now the froth that was drifting on top is this material. So this material is the froth that drifts on top and that forms the crust.
Okay.
This material is very similar to the sort of materials we have at the crust of the Earth, and it's not that easy to recognize. You have to really see the crust of from coming in the atmosphere to tell it's a meteorite by eye. This is called an achondrite. These are pretty rare. Now, if a meteorite is not stopped by the atmosphere, but actually carries some of its tremendous speed with it coming into the atmosphere and hitting the ground, a huge explosion results and an impact crater is formed. So when an asteroid still carries some of its speed that it has in space and hits the ground with that speed, you get this massive explosion and an impact crater is formed. And in the explosion, some of the soil of the Earth is molten, and you get these little molten droplets that are splattered all over the place. And I mean all over the place. There was this big impact somewhere in the Laos and Cambodia area 700,000 years ago or so. The molten rock from that impact is found from southern China in the north to the middle of Australia in the south, and in the Philippines and in the Indian Ocean. So a really big part of the Earth gets splattered. And this type of material is called a tektite. And what it really is a glass. If you hold it against the light, you can see it's translucent, just like the glass is. Now, depending on how much iron there is in the ground, you're going to get either a very translucent glass like this. This was an impact in desert sand, which had almost no iron in it, and so it's called Libyan desert glass, and it tastes nice and transparent. This little piece of glass was from an impact in Germany. It's now found in the Czech Republic. It's called a moldavite. It has a greenish color, so there's a little bit of iron in it. And then this little speck of thing that just looks like a little rock, but if you hold it against the light, you can see it's translucent.
Oh, that's nice.
This little speck had a lot of iron in it. So these are what's called tektites. If you go and visit a site where there was an impact crater a long time ago, and the crater has now eroded away, all the top soil is gone, and you sort of get a cross section to impact crater, you can find all the rock that fell back, all the debris, the breccia. And this rock is a little piece of impact breccia from the Rochechouart crater in the south of France. If you ever get a chance, if you go to Limoges, where they make this nice pottery, or you go to Bordeaux to sip on one of the red wines they're making there, sort of in between that area is a 25-kilometer crater called Rochechouart. It's completely invisible. It's just a landscape like any other in southern France. But if you look at the houses, you can see that they are built out of this stuff. And it's a really strange rock to look at. And it's really created by this huge impact that happened in that area, and that then splattered up, fell back, and created this big pile of rubble. And that's what we can now find and use as a building material. If you go to the little town of Rochechouart, the church is built out of this, and they have a little museum that you can go and visit, and it tells you all about it.